Okay. Okay, let's just zip through these. A lot of these are pretty quick anyway. What about this? Yes or no? No. It is not, is it? Not a polynomial. How come? Got an x on the denominator. Yeah, and if I split that up, I'm going to get 6, which is fine, plus 2 over x, which is not fine. Okay, so there we go. How about that one? No? Good. And the reason being, this guy, right? There's the red flag. That one doesn't work. Okay. How about that? No. And what's the red flag here? Fractional exponent. There we go. Good. Okay, how am I going to do this? I'm going to do a binomial expansion on this, right? So talk me through the process here. What am I going to write down first? Okay, say it again, Grace.
Pascal's Triangle.
Okay, Pascal's Triangle, we could, I would say probably, hopefully, I would try to just memorize the first two rows, you know, n equals 2 and n equals 3. Those are expansions. Those are patterns we just use so much we want to know. Good, so let's start with our template. Let's write down the pattern. So we have the pattern a plus b cubed equals, go ahead, Carson, what's that expansion?
1, 3, 3, 1.
Okay, but keep going. So 1 what?
Oh, 1 a cubed.
A cubed plus
3a squared b
plus
3ab squared
plus b cubed. Okay, everybody good with that? Everybody understands that? Just try, that's a good one to memorize. So now, what do we have there instead? What's our a going to be? What's our a? 6x, okay. So we're getting 6x cubed plus 3 times, what's this term going to be? Ella, what's this term going to be?
6x squared.
6x quantity squared, good, times, there you go. Okay, and we're just going to write out, in order to avoid making mistakes on this, just write it all out unsimplified first, right? In terms of, in the form of our pattern, and then we'll simplify. So then we get 3 times 6x to the 1 times 7 squared plus 7 cubed. And now we just have to simplify each term and we're done. So this is going to give us 6 cubed, which is, what is that, 208? 208x cubed plus 3 times 6 squared, which is 36, times 7. So we could do 3 times 7 is 21 times 36 is going to be 396. You might want to check I might make mistakes here, so double check me on a calculator. Plus, let's see, 3 times 6 is, he won't do it this way. 4 squared, or 7 squared is 49 times 6 is going to be 300 minus 6. So that's going to be 294 times 3. We could just subtract 18. So 900 minus 18. So that's 872 x. Yeah, plus 7 cubed is 343. Okay, is that right? You guys, did you check me? Carson, did you check me on that while I was going? Anybody got a calculator out there quickly where they could do it? Or which one? The first one? Oh, yeah, you're right. Yeah, it is 216. Yep, you're right. Yes. But you see, I mean, even if they're mistakes, you see how we got it? Everything else looked good? Just so we get in our notes right, I guess.
The second term is 756.
756? How did I get so far off?
It's a 6 times 6 and then times 3 times 7.
What did I do wrong there? 21 times 36. Oh, I know. I know what I did. I know what I did. Yeah, I did multiply by the 2. Yeah. Okay. So what is it again?
756.
756 x squared. Man, that was bad math. Other two are right. Okay, good. All right. Well, it wasn't all wrong at least. Okay. So, I guess I had it right there. Shoot, I didn't even think about that. Should have been 882 evidently. Man, I'm not fired. Must be Friday, huh? 882x. Man, well, you got it right there. Okay, questions on that? Does that all make sense? Okay. Okay, so this guy, unless you have this pattern memorized, and really all you need are the coefficients. You guys remember the coefficients from row 4? Yeah, it's 1, 4, 6, 4, 1. Yeah. If you don't remember it, all you got to do is make a quick Pascal's triangle. You don't have to go down very far, though. And Pascal, I know it's kind of a pain. Like, I think, I gave you one on the homework where you had to do one out to like the 7th or something. Is that right? Pretty sure. I think I did. You don't remember? I think I did. And that's kind of a mean trick. I mean, that's just, there's so much. The numbers get so big and there's so much multiplying. I won't make you do that. On the test, you know, just so it doesn't take forever to do the test, I'm only going to go up to probably the 4th or 5th power. Would be the highest I would go on that. But if we crank out a quick Pascal's triangle, it's just going to look like, you guys tell me what to write. What's row 1? Well, it's 1, right? I mean, row 0 is 1. What's row 1? 1, 1. What's next? What's next? Okay, what's next? And that's as far as we have to go, right? Because remember, these are our row numbers. Right? Those are our row numbers right there. And so this is row 4. Okay, so there's the row we need. So then our pattern is just going to be A plus B to the 4th. And we're always going to make that a plus, right? And then B could be a negative quantity. That's the best way to do it. Is going to be coefficients are 1. And then give me the powers with it too here. Grace, what am I going to get for row, or what's this all going to be then? I'm going to get, good, plus, okay, plus, oops, you're right. Okay, plus, okay, good. And then our A is going to be a positive 3y, and our B is going to be a negative 1, okay? So we're going to get the quantity 3y to the 4th plus 4 times the quantity 3y cubed times negative 1 to the 1. Anytime you have a negative factor to an odd power, you know you're going to get a negative, right, on that when you're doing these expansions. That's going to be a negative term then, right? Plus 6 times the quantity 3y squared times the quantity negative 1 squared plus 4 times the quantity 3y times the quantity negative 1 cubed plus the quantity negative 1 to the 4th. Okay, so what's that giving me? 3 to the 4th is 81, so I'm getting 81 y to the 4th plus, or minus, right? It's going to be a minus because I've got that negative 1 to the first power. So minus, what's that going to be? 4 times 27, so 108. What power of y? 3, right? Because I have to take 3 cubed times y cubed. Everybody seeing that? Okay. And I should get a polynomial in standard form. Plus, that's going to be a plus this time because my negative 1 squared just becomes a 1. And then I'm just getting 9 times 6 is 54 y squared. Give me thumbs so far. How we doing? Is that good? Okay. I'm going to get a minus because look at that. That's giving me a minus. 3 times 4 is 12y. And then negative 1 to an even power is 1. Okay. Oh, I guess we have, remember this time, we got answer right there. Okay. Give me thumbs. How we doing? Good? Okay, what's the, they want the degree and the leading term, and that's it. So really, we just want the leading term, and that's going to give us both answers, right? So what's the leading term going to be on this? What's the leading term? Ashton, what do you think? That's right. Good. Because we're getting, this guy is giving us x to the 12th plus stuff. That one's giving us x to the 10th plus stuff. And so when I distribute, I'm getting x to the 22nd plus stuff, right? So our leading term would be x to the 22nd, and the degree is 22, right? Okay, good. Okay, we did this one the other day, right? Any questions on this one? You feel like you're getting the hang of this, graphing these polynomials? Okay. Oh, there's no polynomial shown to the right, is there? Is that the polynomial? Oh, there it is. Okay. Let me put that where we can see it better. How about? There we go. Okay, so how many turning points? Just show me fingers. How many turning points we got? Good. All right, everybody agree 4. How many, oh, where are the X-intercepts? So they want them as ordered pairs. So the leftmost one would be, everybody agree, negative 6, 0, then what? Negative 4, 0, negative 2, 0, 1, 0, 3, 0, right? Okay, is the leading coefficient, A is defined as the leading coefficient, is A positive or negative? Positive, right? And we know that because it's got positive odd behavior, right? Up on the right, down on the left. The minimum degree. So what's the minimum degree given the fact that we have 5 X-intercepts and 4 turning points? It's got to be 5. It has to be odd, doesn't it? Because the end behavior is odd. And so 5 is the answer. Okay, give me any questions on that. Give me 1 to 5 on that one. How we doing? Okay. Okay, any questions? Okay. What's the maximum number of real zeros for the first one? 11. Everybody agree? Okay, which means what's the maximum number of X-intercepts? 11. Maximum number of turning points? 10. Okay? All right, leading coefficient test. Okay, so we want to know, we got to use leading coefficient test here. So we need to know what the leading term is, right? The leading term tells us a lot. So I'll let you guys think about this for a second. What's the leading term going to be? Riley, what do you think? Leading term? That's right. Yeah. Okay, that's giving us a negative 2x cubed times an x cubed times an x if I just multiply all the leading terms, which is all we need to do, right? Okay. So then what's the graph end behavior look like on this? Show me with your arms. What's that look like? If it's negative 2x squared. So if it's x squared, it's even, so it's got to be this, doesn't it, right? Even means same end behavior. That's positive even, negative even, right? Odd is opposite end behavior. So the shape is like that, okay? What are the X-intercepts? Okay, what are the X-intercepts? Give me one X-intercept, 0. Okay, we're getting what else? 3. What else? Okay, those are our 3 X-intercepts. Good. Okay, so what does the graph do at x equals 0? Does it cross the x-axis or does it touch and turn? Crosses, good. So it's going to cross. Now, we talked about this a little more specifically than the textbook did. Not only does it cross, but what's it going to cross like at 0? Yeah, it's going to cross like a cubic, isn't it? It's going to graze and turn, right? So we know if we included a little picture there at 0, it's going to cross like this, right? If this is the x-axis, it's doing that, isn't it? Now, we don't know if it's coming down from the right or down from the left, but that's the basic shape, right? It could be reversed. What's the graph doing at the rightmost 0, which would be 3? Everybody agree it's bouncing? Because we've got even degree. Oh, there we go. Okay. So we got a picture like this then for this guy. And then finally, what's it doing at the leftmost 0, which is negative 5? Crossing, so it's cutting like a line. Yep, good. Okay, so picture here, that was orange. So doing that, right? Okay. Find the Y-intercept. Okay, how would I find the Y-intercept? Yeah, everybody agree? Y-intercept is just f of 0, right? So what's that giving us then? If I'm evaluating this at 0, well, what's the answer going to be? It's going to be 0, isn't it? Because I'm going to get 0 times negative 3 times 5. But the first factor is going to go to 0. So it's 0, right? Okay, now symmetry. And I am going to put one of these questions on the test. So there's going to be a little piece of symmetry on there. Just because, I mean, wouldn't you agree? Like this is, rate the difficulty of this on a 1 to 5 compared to other stuff we've done. Like 5 being the most difficult, 1 being the least difficult. I mean, don't you think it's kind of like a 1 or a 2 at the most, right? Or I mean, it's really pretty. This is just kind of, this is a pretty easy one. Next test is a little more challenging than this one is, right? But just to give you something a little bit more, a little bit more sink your teeth into, a little bit more, I included something that's not really normally part of the curriculum. We're going to do the symmetry thing, right? So determine whether it has y-axis symmetry. What kind of symmetry would that be? What did we call that? Do you remember? Y-axis symmetry. If it's a line, it's got to be folding symmetry, right? Think what you can do if you're talking about symmetry about a line, which the y-axis is. It's got to be line symmetry or folding symmetry, right? So that's what we called even symmetry. Origin symmetry, that's a point, so it's got to be rotational symmetry, right? That's what we called what? Odd. Okay? And let's remind ourselves real quick what the tests for symmetry are. For even symmetry, the test is f of negative x equals what? Say it again. It's the same, so it's f of x. Yeah. How do you remember that? There's a really easy way to remember that. If you think about it in terms of the simplest function that has even symmetry, that's just y squared, right? So if I go over some distance x, right, so we're calling that x, then the coordinates of that point are x, y, right? X squared, right? Y just equals x squared. If I go backwards, negative x, what's the height? Well, it's the same height, isn't it? Everybody see that? Look at that. The y values are the same, right? Everybody get that? Okay, so there's your test. F of negative x equals f of positive x. They have the same outputs. Okay, now compare that to, what if we're graphing the simplest odd function that's not a line? Y equals x cubed. If I go over x, I'm going up some amount y, right? If I go backwards x, I'm going down by that same amount, right? So this is telling me f of positive, or f of negative x equals the opposite of f of x, right? Give me thumbs. Does that make sense? Okay. So those are our two tests then. F of negative x equals f of x is even. F of negative x equals negative. F of x is odd. And we just have to test and see, right? We have the function here, so let's just evaluate our function at negative x and see if we get either one of these two things happening. If we get one of those things, then it's conclusive. If we get neither of those things, then there's no symmetry, right? Well, at least neither one of those types of symmetry exists. Okay, so if we run this through, f of negative x is going to give us what? Well, the first term is going to be negative 2 times the quantity negative x cubed times negative x minus 3 squared times negative x plus 5. Okay, so suggestions how we could tell. What could I do here? This is a little bit trickier because I mean the The surefire way to do this would be to write it as a polynomial, wouldn't it? I could expand this whole thing out, and then even and odd symmetry, remember where that comes from. If you have a polynomial with only even powers of x, it's guaranteed to have even symmetry. That's why we call it even symmetry, because we're thinking polynomials here. If we have a polynomial that has only odd powers of x, then it's got odd symmetry. If it's got even and odd, it all goes away. Neither one of them works. Okay? All right, so what do you think? What could I do here? I mean, I don't really feel like multiplying that whole thing out. That's a lot of work, isn't it? Right? Could we make a prediction, though? If I were going to multiply this, whole thing out, could you, I don't know, you guys talk to me. Tell me, just use some logic here. See if you can come up with a tricky way of doing this without having, and we could multiply the whole thing out. We really could. I mean, honestly, it wouldn't be that horribly difficult to do. It's probably going to take you about 5 minutes, though, of just cranking out some math, right? What's some thinking here where we could conclusively determine if it has even or odd or neither? Think about that for a second. What do you think? See if you can come up with some really clever way of doing this. I can think of a couple reasonable approaches you could take without having to multiply the whole thing out. You could. Yeah, you could. You could try to determine, and you can do that. Well, what's your thinking on it, Carson? Okay, and how come? Oh, you mean in here, you mean?
Yeah.
Okay, but having both even and odd, let me see if I can think of an example where that falls apart. I can't think of one off the top of my head, but here's potentially the issue with that. If I were going to expand all these out, how can we guarantee that when I'm adding like terms, I don't get some cancellation and like, you see what I'm saying, powers of x could potentially fall out because of cancellation. Like, what if when I multiplied it out, hypothetically, I ended up getting negative 2x to the fourth, plus 3x cubed minus 3x cubed. See what I'm saying? Could that happen, right? Maybe. So we can't assume just because I've got even and odd functions of quantities that are being squared that I'm necessarily going to have even and odd powers of x when I expand it all out. Okay? This is good. I like discussions like this. It's not a bad idea, though. Anything else? Any other ideas? And keep in mind, we could just multiply the whole thing out, right? So we're just trying to see if we can be really clever about finding a shortcut. Okay, I'm going to give you a hint here. It's not going to be a very big hint, but maybe this will guide your thinking a little bit. So in order for this to be even symmetry or odd symmetry, how many values of x have to exhibit that behavior? Where, how many? More than 3. Say it again. All of them, right? If I put in a negative value of x and it's even symmetry, I would have to get the same output as when I put in its positive opposite, right? Everybody agree? It'd have to work for every conceivable value of x. That would have to be true, right? If it's odd symmetry, every time I put in a negative value, I would have to get back the opposite. Did I say opposite last time? If I did, I didn't mean to. If I put in a negative value and it's odd, any negative value should give me back the opposite of what I get when I plug in the corresponding positive value, right? So they would all have to work. How many counterexamples would I need to disprove either one of those hypotheses? 1, right? So all I've got to do is find a single value of x to prove that it's not even. All I have to do is find a single value of x that does not give me back the same value when I put in a positive or its opposite negative, right? If that's true, if I can find even one, it's not even. To prove that it's not odd, do the same thing, right? Does that make sense? If I find out that it works, if I arbitrarily got one, now does that mean if I plug in a single value of x and it seems to be even, does that prove it's even? It doesn't, right? But really the best we can do here is prove that either it's neither, is what we're looking for. If I can show that it's neither by picking a point, then I can avoid having to do a whole bunch of work. You see the logic there? Right? What's your intuition? What do you think it's going to be? Probably going to be neither, isn't it? Right? Carson's line of reasoning is probably going to pay off. We just can't guarantee it logically, right, without doing the work. Okay, so let's just pick one. Pick one that's not horribly difficult to plug in. 1. There you go. So how about if we try f of negative 1? Let's see what happens. Well, let's do f of 1 first. F of 1 is going to give me, if I plug that into my function, the first factor is going to be negative 2, right? Next factor is going to be, I'm going to get 1 minus 3 is negative 2 squared is 4. Last term, 1 plus 5 is 6, right? Okay, let's try f of negative 1. F of negative 1 is going to give me positive 2, right, times negative 4 squared is 16 times 6. Are those either going to be the same or opposites? They're not, are they? Right? The brown output and the pink output are not going to be the same, and they're not going to be opposites. Agreed? So we just showed that it's got to be neither then, right? Because we found one counterexample to both the even and the odd hypotheses, right? The tests failed for a single value, and so therefore they fail. Make sense? Okay. That's actually a pretty good discussion. That's logically, that's a good line of reasoning to use in mathematics when you're doing proofs. Okay. So then what would the graph look like finally? Okay, so we know we had X-intercepts we had a green one at 0. When are we out of here? Oh, okay, we'll do this last part later.